So hello everyone, this is lecture 44 for the mathematical physics. In the last lecture we have studied about the Lorentz series, and I told you that Lorentz series is the series expansion around a non-analytic point. Okay, and there was Taylor expansion that was around a analytic point. Okay, so today we will see about the zeros and the singularities. So they are related to the Taylor series and the Lorentz series. So let's see how. So first we will study about the zeros. So zeros are defined for an analytic function only. So what is the meaning of zeros? So you know, if it is defined for the analytic function, then we will discuss about the Taylor series. So if fz is given by this, so it is a analytic function, so we can write any function which is analytic in this form, which is Taylor series. So here fz is analytic within some reason if fz vanishes at z equal to z0. Now this fz, this series, if vanishes at z0 point, then point z0 is said to be the zero of fz. Okay, so this is the definition of zero of an analytic function. So at a point at which the series collapses to zero or vanishes, so we will say that point is called the zero of fz. So let's say the series is like a naught z naught and in z minus z naught 1 0, then a1 z minus z naught 1, a2 z minus z naught 3. That's how it will go. And say let a naught equal to 0, a1 equal to 0, and it will go like that. And the last am minus 1 is 0, but am is not equal to 0. So at any point means let's say we have a naught equal to 0, a1 equal to 0, but a2 is not equal to 0. So we call that 0 of second order. Okay, means then fz is said to be have 0 of order m. So at which it is non-zero, so we will say that the fz is said to have the 0 of order m. So let's take some examples. First, you know what is an here. So by the Taylor series expansion, you remember the formula. That was fn z minus z naught divided by n factorial. Means this was z naught and inside was this. So in the place of an, you will write this fn z naught divided by n factorial, where fn is nothing but differentiation of fz of nth order. Okay. So let's see some examples. It will be more clear to you then. What is the meaning of this order of 0? So let a not equal to 0. That means fz not equal to 0. Means we are expanding this. So a not equal to 0, fz not equal to 0, but f dash z not is not equal to 0. Okay. So we have first term equal to 0, but this first derivative term is not 0. So we'll call this as order of 1, 0 of order 1, or simple 0. Okay. Like here you see a not equal to 0, a1 equal to 0, a2 is not equal to 0, so it will be 0 of second order. Means you will get f z not equal to 0, f dash z not equal to 0, but f double dash z not is not equal to 0. So z not is order of 2. So at the point where this function is not becoming 0, so we will call this the order of 0. Okay, so let's see one example, then it will be more clear. So let's say we have fz equal to 1 plus z square. So fz will be 0. Let's see at what points this function will be 0. So to find the zeros, first we need to find the points at which this fz is 0. Then we will see that what is the order. So first the points at which it will be 0. So 1 plus z square should be 0. So z is nothing but plus minus iota. So only these points this function will be 0. So these are the zeros. Now what is the order? To find the order, we will first find the derivative f dash z. So it will be 2z. Now see, if you put the plus minus iota here, then it won't be 0. So this first term is not becoming 0. Only this term is 0 at these points. So we'll call this as plus minus iota are order of 0 of order 1 or simple 0. Order 1 or simple 0. If you get this f dash z equal to 0, then you will take the f double dash z. And if f double dash z came out to be non-zero, but these two terms are 0, so we'll call this as 0 of order 2. Let's take one more example. Fz equal to 1 minus z4 to the power square. Now this function is 0 at z equal to plus minus 1 or plus minus iota. So these are the zeros of this function. So let's see the order. So first f dash z will be 2 1 minus z4 1 minus 4z cube. So this will be the differentiation. Now substitute these values, so it will be 0 again. So let's find the next order derivative. F double dash z, if you find, means the derivative of this, then that will not be 0 at these points. Means whatever you will get, that will not be 0 at these points. So we'll call these points as R zeros of order 2. Okay. Now let's take one more example. Fz equal to z minus a cube. So it will be 0 at z equal to a. So this is your 0 of this function, that is z equal to a. So f dash z will be 3z minus a square. Now this is also 0 at z equal to a. So let's find next order. F double dash z will be 6z minus a. So this will also be 0 at z equal to a. So let's find next one. F triple dash z will be 6. Now this is not 0 at z equal to a. So this is your 0 of order 3. So that's how you can find. And this zeros are only for the analytic functions, remember that. Now if fz equal to exponential z, then this function can't be 0 at any point, so this has no 0. If take fz equal to sin z, then this will be 0 at z equal to plus minus n pi. Now this will be, let's check if it will be simple or what is the order of this 0. So the first derivative will be cos z, and cos z at these points will not be 0. So it will be a simple 0 or the 0 of order 1. Okay. Now if fz equal to sin square z, then again z will be same, zeros will be plus minus n pi, but let's find the order. So first order derivative will give you 2 sin z cos z, so it will be sin 2z. So sin 2z will be also be 0 at these point. So f dash z is 0, but f double dash z will not be 0, so it will be order of 2, means this is a 0 of order 2. So you can check them, these are very easy things. Now we done with the zeros of our analytic function. Now we will talk about the singularities. So singularities are defined for a non-analytic function. So these are the points at which a function is non-analytic, is called singular points. So like you have fz equal to 1 upon z. So at z equal to 0, this function is diverging. So we call this point as, means at z equal to 0, this function is non-analytic. So this is called the singular point. Z equal to 0 is singular point for this function. Same if fz equal to 1 upon z minus 1, z minus 2, then z equal to 1, z equal to 2 will be singular points for this function. Now we have two kinds of singular points, the isolated singular points and the non-isolated singular points. So what are isolated singular points? When there you have any singular point and there is it will be non-singular or the analytic around this point, but only non-analytic at this point. So we'll call this as isolated singular point. But if all neighbors of this number is also making the function as non-analytic, then we call as non-isolated singular point. So if at z equal to z naught, function fz is non-analytic, but it is analytic at all neighboring points, then z equal to z naught is identified as isolated singular point. So you get the thing, means here you can see the example. At z equal to z1 and 2 are isolated singular points. Okay, because if you take any point around 1.1, 1.2 and 2.1, 2.2, then you will get a analytic function. So that's how you can say that this is the example of isolated singular point, this one. Now this is an example of non-analytic. So we will take the Laurent expansion definitely for the non-analytic points. So now you will find the poles. In the zeros we have find the order, and when you have singularity, so you find the pole of singularity. So if we write Laurent expansion about z equal to z naught, then it contains finite number of negative powers. So we discussed about the Laurent series, you were getting some negative terms of z, 1 upon z, 1 upon z square. So these are because of the non-analytic points. So that define the pole of function or the singularity. So it contains finite number of negative power of z minus z naught, that is z minus z naught by minus n, when n is not equal to 0, and this is finite, this n value is finite. So in this, singularity is called pole of order n. So whatever n value you are having, maximum negative term, so that is called the pole of order n. If n is equal to 1, then z naught, this singularity will be of simple pole. If n equal to 2, then singularity will be pole of order 2. So it contains infinite terms of negative powers. If you have the infinite terms of negative powers, means it will go like this, 1 upon z square, 1 upon z cube, and it will go to infinity. Then this is called the pole of infinite order, and we also call it essential singularity. Then z equal to z naught is called the pole of infinite order or essential singularity. Now there are also non-isolated singularities and the removable singularities. We will discuss about them, but not here, not today. So this is the first way you can find the pole, means you can check the maximum negative power. Or there is one more easy way to find the pole of singularity. So you just need to put this limit, whatever function you are having, just put the z minus z naught n, so that this should be putting like that. You will get a means you will get an analytic function after substituting this. So the minimum power of n will be your order or pole. Okay, so this should come out to be finite. For that minimum n, you will call that as your pole. So let's see an example, it will be more clear then. If fz equal to sin z over z4, now it is singular at z equal to 0 and it is isolated singularity. So how we can put the limit this way so that this singularity is removed? So if you put z, means this value should be finite if you put the limit. So how you can put that? If z cube is there, then you will see that z cube will cut out it and will give you sin z over z, and that is 1. So you can substitute that value so that you can finite value. You can get finite value. So z minus 0 cube and z tends to this 0, z naught, sin z over z4. So this will give you 1. So this minimum power is 3. So you will get the value of n equal to 3. So it will be pole of order 3. Same you can solve it by the Lorentz series expansion. You know the expansion of sin z is z minus z cube by 3 factorial plus z5 by 5 factorial and so on. Multiply this inside and you will get the maximum negative power as minus 3. So this is how the same result you will get, n equal to 3. Here also you will get n equal to 3. So let's take one more example for this kind. It's like fz equal to 1 upon z square minus 1. So it can be written like z plus 1 z minus 1. Now to make this finite, for z equal to minus 1, first let's take the point of singularity z equal to minus 1. So for z equal to minus 1, limit should be go z tends to minus 1. And if you put here z plus 1, then it will give you finite value. So z plus 1 to the power 1, so it will cancel out and it will give you a finite value. So your pole of order will be 1, means simple pole, because for 1 power you are getting a finite value. For z equal to plus 1, you will substitute what here? Z minus 1. So z minus 1 will cancel out this and you will get your finite value 1 upon 2. So this will be again simple pole. If you need to put here a square of this, then you will get the simple second order pole. And if you need to put here 3 to make it finite, the minimum value you need to put here to make this thing finite, then you will get the order as, or the pole of order n. Okay, whatever power is here. So let's take one more example. Something like fz equal to 1 upon z square plus a square to the power square. So this can be written like this: 1 upon z plus iota a, z minus iota a, and square of both terms. Now what are the singular points? So at plus minus iota a, you will get your singular points. So for the plus iota a, you can substitute here z minus iota a square. So this will cancel out this. So that's how. So for plus iota a, you will put here this, and this will cancel out this, and you will get a finite value. So it is of order 2. So it is called the polar. This is singularity of pole of order 2. Same for z. If z equal to minus iota a, then you will get z plus iota here, and it will cancel out this plus term. And in the minus term, if you put the minus iota a, you will get a finite term. So that will also be the pole of order 2. Okay, singularity of order 2. So that's how you can find the pole directly using the limit. But also can you find from the Lorentz series expansion. So fz equal to z exponential 1 upon z. So let's solve this. Exponential 1 upon z will be 1 plus 1 upon z, 1 plus 2 factorial z square, and that's how you know the expansion. So multiply z inside, you will get z plus 1 plus 1 upon z, and this will go to infinite. So this is the example of essential singularity or infinite order. So I already told you about this. Pole of infinite order and essential singularity. Now, if fz equal to sin 1 upon z, the next expansion will be this. This is also going to the infinite. So it is also a essential singularity. Z equal to 0 is essential singularity. Now fz equal to 1 upon z, z minus 2 square 5 plus 3 upon z minus 2 square. So it is singular at z equal to 0 and z equal to 2. So you have 2 points and these are isolated singular points. So let's first check for the z equal to 0. For z equal to 0, you need to put z minus 0 here and put the limit z tends to 0. Now this z will cancel out here and you will get here 3z z minus 2, and substituting z equal to 0, you will get your finite value, that is minus 1 upon 2 5. So this is simple pole. Now for the second isolated point, that is 2. For 2, what you need to multiply to this whole term so that this singularity is removed. So you need to multiply z minus 2 5. Only then this will cancel out and this 2 will give you 3 here. So you don't have anything in the denominator which is becoming 0. So you need to multiply with z minus 2 or 5. So this is n equal to 5. So this is a singular point of order 5, means pole of order 5. So that's how you can find. There are many examples of this. Let's take one more example. This is the last example for today. So if fz equal to 1 upon sine 1 upon z, then this, to make this, the singular points will be, to make this 0, so 1 upon z should be plus minus n pi. From here z will be plus minus 1 upon n pi. Now see this, these are the all points of where this is becoming 0 or the singular points. Now see z equal to 0 is a singular point, and you will see that 1 upon, for n equal to 1 it will be here, 1 n equal to 2 it will be here, and for n equal to 3 it will be here, and this distance is becoming less and less. So when you came to the nearby 0, you will get infinite number of singular points around 0. So see, this z equal to 0 is a non-isolated singular point now. Okay, for this example, this is the example of non-isolated singular point. So z equal to 0 is a non-isolated singular point because it has, in all the neighboring of this will have the singular points. Okay, that's why this is non-isolated. So you can see this distance is becoming less and less, and you will get infinite terms here which is singular points. So that's why it is non-isolated. So that's all for today. In the next lecture we will see about the removable singularities, where we can remove singular points. Then we will discuss about the branch point singularities, means you will have z to the power fractional powers or under root of z and all. So we'll discuss all of them. So let's end today's lecture here. Thank you everyone.